In this lecture, we are going to start talking about a new topic, which is side effects in programming, and in particular, side effects in the context of programming in OCaml. Before we actually get into talking about the details of side effects, let's try and understand why we might want something like side effects. The catchword is communication. So up to this point, the kind of communication that we've been become used to is one that is based primarily on expression evaluation. So for example, if you are talking about a big process, it might carry out its computation by breaking up that process into smaller processes, which then corresponds to expressions, and these expressions carry out some evaluation and produce a value back. So that's a form of communication. Similarly, the user might want to carry out a certain computation, and what the user does is type in an expression, and after the dust settles, what the user gets back is a value. Right? So once again, that value comes from expression evaluation. And so in this sense, you can think of expression evaluation as being the primary mode of communication. This works well in lots of situations, but sometimes it's not the most natural model to use. So some examples where it might not be a natural model to use are the following. First, the kind of communication that we are talking about that is taking place through expression evaluation is one where the communication is between a parent process and its child processes. But sometimes the communication that you might want to happen needs to be between sibling processes or sibling expressions. And for this, we might need something other than just expression evaluation as a means. Another kind of situation in which we might want a communication that is not covered by expression evaluation is that where the communication is with an external process. For example, you might want, in the course of a computation, you might want the user to provide you some input, so that then based on that input, you could drive the remaining computation or the further computation. Another example of a situation where you might want to interact with an external device is when you want to write or read into files. Why might you want to do this? Well, one reason might be that you want whatever is produced to be permanent, right? You may not want it to go away once the program is finished. Right? So for that, you'd have to communicate to some kind of permanent storage, which would be a file. And another situation in which writing to a file might become important is when the data that you want to communicate is voluminous. Right? If you're running a process, over time it can produce a lot of data. And maybe this entire data that it produces needs to be passed on to some other process. So in that case, it may not be feasible to pass it directly in main memory. What you might want to do is store it in a file and then invoke the other process and run it on that file. Okay? So here again, we need a mechanism for communication that allows us to write something into a file, or write something out, communicate with an external process. And a final situation where the communication between a parent process and the child process doesn't suffice is where there's no natural way to finish a computation that a child process is being invoked to carry out. Right? In this case, there isn't any sense in going back to the parent process, because what the parent process needed cannot be done. So here's a situation where you probably want to fail in your computation all the way back to a point where someone knows what to do when that kind of a failure occurs. Right? So typical examples of this kind of behavior or phenomenon is when you're asked to carry out a division. So there's an expression that involves a division, and the denominator turns out to be 0. So if it's 0, you cannot actually carry out the division. You actually need to fail back. You need to raise what we refer to as an exception, and the parent wouldn't know how to deal with that exception. It goes all the way back to some earlier process which actually is able to handle these kinds of exceptional situations. Right? Has been set up to handle these kinds of exceptional situations. And exceptions of this sort can occur also from other kinds of phenomena. For example, you're trying to read an integer from the input, and in fact, there's no integer present there. There's only a string of alphabets. Right? So this is a situation where um, you can't really read that input, and so you have to raise an exception and break out of the computation. Okay, so these are some of the different kinds of things that we would like to consider, which sort of go outside the pattern of communication via expression evaluation, and we deal with them through side effects or constructs that allow us to uh, carry out side effects. Okay, so we'll understand these constructs, uh, and then we, in the course of it, we'll also understand a little about how to use them systematically in programming. So in this lecture, I'm only going to talk about the first aspect, that is this one, where we are dealing with communication between sibling expressions or between components of a sibling expression that might be nested more deeply in the sibling expression, etc. So in this context, we'll introduce this notion called state, right? And we'll introduce constructs that allow us to manipulate state. Right? And in the next lecture, we'll take up the other two aspects, which is that of I/O and exceptions. Okay, so let's get started on the first aspect. So let's revisit the kind of communication I was talking about a few minutes back. So typically in OCaml, what happens is that you try to evaluate expressions, and expressions have the typically have the form that is shown out here. Right? It may be one expression, maybe one applied to another, it may be one applied to many, and so on. But the general structure is captured by this. So here, there is a parent process that wants this expression, which consists of two composite expressions, right? E1 and E2. It wants it to be carried out. Okay. So here we can see that there's one form of communication that needs to take place, and that is between the parent process and the two sub-processes represented by E1 and E2. Right? So we need communication between the parent process and E1 and E2, and this actually has a fairly natural treatment in OCaml. So what is the treatment? Well, the parent process passes information to E1 and E2 essentially via parameters. Okay? So E1 and E2 might be processes that need to carry out some computations, and the kinds of computations that they need to carry out might be sensitive to information that is provided by the parent process, and this is provided through parameters. And the converse, which is when E1 and E2 are finished, when they need to pass back some information to the parent process, they will do it essentially by generating a result which then goes back to the parent process. Okay. So this kind of communication is handled perfectly well by the expression evaluation model. However, there might be situations in which one wants E1 and E2 to communicate. Right? So E1 is doing some task, and part of that task is sort of determining certain aspects of the task that E2 has to do. And so it's going to generate some information that needs to be passed on to E2. So how should we realize this kind of communication? Well, one way to do it is to orchestrate this communication between E1 and E2, and in general between sibling expressions, essentially through the parent. So what happens here is that the producer, which in this case, in the case of our example, happens to be E1, it returns a value to the parent expression, and then the parent expression knows that this value has to be passed on to the consumer, and so it passes it on as an additional parameter to the consumer. Right? So we can, in principle, accommodate this kind of communication between sibling processes, sibling expressions, via the existing model. The problem with this approach, though, is that when you're designing the parent process, you not only have to consider the task that needs to be carried out overall by the parent process, but you also need to get involved in this aspect of how to orchestrate the communication between sibling processes. Right? And then the latter is somewhat orthogonal to the main purpose of the parent process, and so it can end up cluttering the conceptual space. Okay? So what would be a solution to this? Well, one solution might be the following. What we do is we let the parent uh, play a role in the communication, but free the parent of thinking of any of the details related to the communication. So uh, we can do this essentially by introducing an auxiliary component uh, to the computational framework, which we call a state, right? And what is happening is that the state is something that can be affected by any process, right? And uh, so the sub processes might affect it and might use it. And essentially what the parent process is doing is it's passing the state between sibling expressions. So concretely, uh, in the producer, what you might do, like in E1, you might carry out some kind of computation, and then there might be constructs which allow you to say that there's a component in the state which is called X, right? And what I want to do is change the value of that component in the state, right? So the state might have a bunch of variables, right? X, Y, Z, whatever, right? And what we have in this framework is some construct, right, that allows you to change one particular component of the state, okay? And so if through this process of changing one component of the state, you basically affect the overall state. And then you go on, finish the computation, and then you're done, right? And so now once you're done, not only do you return the result of your computation, you also return the state component, right? And then the parent takes the state, passes it on to the consumer, which in this case would be E2, together with the other parameters. Note that the parent has not paid particular attention to which component of the state has been affected by the producer. It just knows that it might be affected and it passes it on to the consumer. And then the consumer does its own computation. At some point, it might need to do, might need to use the state, might need to use whatever the producer had produced. So then it doesn't look up like expressed in this kind of an expression. So it looks up the X in the state and carries out whatever operations it needs with it, and then goes on and finishes its task. And then once it's finished, it returns its result together with any the state which might contain some further modifications that the consumer itself might have made. Okay. So that's one way to think of how communication between producers and consumers, which may be far apart in expressions, need not have the parent-child relationship, right? That can take place, right? Basically through the state component. Now, we've seen a systematic way to realize this treatment of state already, right? We saw this in the context where we were trying to model the constructs of an imperative programming language using OCaml, right? And I can sort of sketch out the contours of this. So, and it's also something I've been talking about in the last few minutes, right? So what we do is we add an extra parameter to all functions. This parameter represents the state, right? So the function gets this state as an argument, and what it does is it carries out certain computations within it, and then when it returns a value, it also returns the state as a component of the return value. And within the context of the function, if you need to change the state, you change it by essentially accessing a particular component of the state and making modifications to it, right? And so whatever modifications have been made within the body of the function to the state, because the state is being returned, those modifications are returned, and so the function will act as a producer in this context. And similarly, the function might need to use the state. So in this, when it's using the particular component of the state, it's playing the role of a consumer, and you can just access the data, right, and use it. Right? So if you recall the discussions that we had about modeling imperative programming constructs, we had two notions. One was that of putting a variable, right, and the other one was that of getting a variable, which is basically changing a component in the tuple or looking up a component in the tuple. So those are the two things that play a role in these talks. Okay? And the other two should be fairly straightforward to understand. Okay, so all this seems to work well conceptually, right? Because in this process, the parent, in this kind of approach, the parent process doesn't need to actually worry about how to orchestrate a communication between different pieces. All that it needs to do is it just needs to know that it has to pass the state around. Okay? The problem with this approach, though, is that treating states explicitly in this way can be quite costly. Right? So you might want to modify just one cell in a state which has, let's say, 100 cells. You have to create a new piece of data which has 100 cells in it, because that's the way things work in the functional setting. Right? If you modify one piece, you have to create something that represents the whole tuple, right? And so you have to change all 100 pieces. So the question to ask is if you can do better than this. Okay, so we look now at how OCaml realizes this idea without paying the cost for it. Okay. Okay, so what OCaml does basically is it provides you a means for modeling state implicitly. So there are essentially four components to this, the treatment of the implicit treatment of state that eventually leads to an efficient treatment of it. Okay. And they're the following. The first thing is that the state is treated as essentially as a collection of cells, each cell having a type associated with it that is allocated in a data area called the heap. So let's look at this pictorially, just to get a sense of how things are working, so that we can understand the other pieces of the solution fairly clearly. Okay, so let me stop sharing here and start up sharing on the white, so that I can have a whiteboard on my iPad. Okay, so here's the idea. Okay, so we have something called a heap. Okay, this is a large space. This itself doesn't constitute the state. What happens is that periodically, what you do is you create cells in this in the heap, like that one, that one, that one, and so on. And where exactly they are in the heap doesn't matter. It's just that there are maybe at a certain point 3 cells that constitute the state, okay, that are important. And when you create these states, you also say associate with them a type for the value that can be stored in it. So, for example, that cell might be one in which you are only permitted to store integer values. This one might be something in which you can store integer list values, right? And this one might be something in which you are allowed to store Boolean values, right? Okay. So at any point, at a point where these are the only 3 cells that you created that are accessible, then the state is given essentially by the contents of these cells. And how do we determine which cells are accessible? Well, here comes the idea of a reference. Right? So what you do is you provide access to these things essentially by references to the cells. Right? And these references, right, are essentially what identifiers get bound to, right, through let bindings. So there might be an X, which is going to be a reference to this. There might be a Y that's going to be a reference to this. There might be a Z that's going to be a reference to this. These are all, they're not variables, they're identifiers. So this X, Y, and Z, as identifiers, they are not things that can be changed. But what can be done is that we can change the values in the cells. So for example, if this was 5 at some point, we can basically change that to a 7, right? So we can change the values in those cells. So in this sense, you can update the state, right? And to update it, you have to go through the identifiers, which are references to the cells. So what remains for us to see is how exactly this idea plays out. Okay, what are the constructs that allow us to realize this kind of a model? So let's look at that, and let me get back to the slides for this purpose. Okay, so we have the model in mind. So let's look at the pieces that we have to realize, uh, that we need to realize this model in practice. Right? So we've already talked about the heap and how it has cells in it which have a type associated with them. So now the first question that we ask is, how do we create cells, and how do we type them? Right? Well, the, what we do, what OCaml does is it provides us constructors for creating, for associating a type with a reference, right? That ends up telling us what uh, type can be stored in a cell uh, that is being referenced, right? This is how it associates the type with the cell, and then so to realize this picture, one thing that you need is a type constructor, right? The from a type gives you a reference to a cell of that that can store that type. So the type constructor in OCaml is called ref, right? So it takes one argument, which is a type, and when it's given that type, it gives you a type of references to cells that can store a value of that type. So as a concrete example, you might have a type like int ref, right? So this is ref being given the type argument int, and it corresponds to the reference to a cell in which you can store an integer value. But how do you create the cell itself? Well, for this, what OCaml has is a value constructor called ref, right? Uh, and what does the value constructor do? Well, it takes, or it's given uh, an object of a particular type, right? And what it does, okay, is it creates a cell in the heap, right, in which it puts that value, and then it returns a reference to that cell, right? So concretely, ref is something that takes some value of type quote A, so ref is polymorphic, right? And then what it does is it has a side effect, it creates a cell in the heap, and then it returns a reference to that cell. Okay, so the type out here is a type of a reference to a cell in which a value of that type can be stored. Okay? So let's take a look at an example to solidify our understanding of this construct. Okay, so here's the example, right? So I have a let binding in which I'm binding an identifier called X to something. And what is it that I'm binding it to? I'm binding it to whatever is the result of evaluating this expression. And what's the result of evaluating this expression? So if you pay attention to what I said earlier, ref is going to be something that's going to create a cell in the heap, right? And in that cell in the heap, it's going to put the value 5, right? And then it's going to return a reference to that cell. Okay? That's basically what X gets bound to. So this is what you see displayed by OCaml when it's finished processing that let binding. So what it's telling us is that it now knows of an identifier called X. The type of that identifier is int ref, right? And X is in fact a reference to a cell whose contents are going to be 5, are 5, right? So this is how the process of creating a cell and returning a reference in the heap and returning a reference to it, and also sort of associating the type with the cell gets played out. Okay, so this is one thing. What do we need next? Okay, so the other two components that we need are that of looking up the cell. Right? This is like the put I, except we want to deal with it in an implicit fashion, in a more efficient fashion, right? So we need something for looking at the value in the cell or dereferencing the reference. And then the other thing that we would want is a way of updating the contents of the cell. Okay, so these are the next two things to look at. Okay, so the process of to dereference a cell, OCaml provides a prefix operator that's written as a bang, right? Which has the obvious type. So what bang gets is a reference to a cell in which a value of type port A can be stored. And when it's got this kind of an argument, what it's going to give you is it's going to do a lookup and it's going to give you back the object that was stored, that is stored in that cell. So it's going to be an object of type port A. Okay, so let's look at a concrete example. So we've already got an identifier that is bound to a reference called X that is bound to a reference to a cell that contains 5. So the example now is that of dereferencing X, right? So if you do bang X, right, if you follow the logic of what I had explained, it was the meaning of bang a minute or so ago, you're going to get back the value 5, right? So this is basically what OCaml is displaying to you. It's saying the lookup has yielded a value of 5, which is of type int, and since you aren't binding any identifier here, right, it's basically bound an unknown identifier, right? Okay, so that's essentially how dereferencing works. The other thing that we said was that of changing the value, updating the value in a cell. Okay, and for this, OCaml provides an infix operator := that we can read as gets or assigns, right? So this operator, right, what it does is it takes an identifier or an expression that has type port A ref. So it's a reference to a cell, okay, that of a certain that can store a value of a certain type, and then it also takes as a second argument a value of that type, and the impact of this : or gets operator is essentially to update the value in the cell that is pointed to or that by the first argument, right? It needs to update it to the value that is given to it in the second argument, right? So it carries out this side effect. And notice that the only purpose of this gets operator is to carry out the side effect. So after it's carried out the side effect, there isn't any value to return. And this aspect is realized by saying that this : gets operator has a return type of unit, right? So this is perhaps the first place that we've encountered where we have an expression whose value is unimportant. The only purpose for it is to carry out a side effect, right? So we're seeing the use of the unit type that we encountered a long time ago. Okay, so let's look at a concrete example of how this works. Okay, so we have a cell that is pointed to by the identifier X, in which we have stored 5. Now we want to change it to 7, and here's how you do it, right? So you write X gets 7, and you can see that X is of type intref. This expression is of type int. So the types have worked out fine with : right? And this kind of type checking is something that OCaml will do, right? So it's a strongly typed language, and side effects are not breaking that aspect, right? So it'll at the end of evaluating this expression, it's going to realize the side effect of changing the value in the cell that is pointed to by X to 7. I should have written this down out here. I should have demonstrated that that's what happens by doing a bang X after. Okay, but I'll let you work this example out offline. Right? If you do a bang X after this, what will get displayed to you is the value 7, which will be of type int. And the other thing to note is that once the purpose of this assignment is only to carry out the side effect. So once that is done, OCaml will come back and tell you that the return value is of type is unit, which is of type unit, right? As expected, right? And then it's ready for the next expression that you wanted to deal with. Okay. Okay, so those are the mechanisms that we have for dealing with state. So we have this idea of a state which is realized by a collection of cells which have types associated with them in the heap. And then we have a mechanism for creating cells in the heap. This is ref. We have a mechanism for typing references to cells in the heap. Right? This is the type constructor ref. Right? And we have mechanisms for looking up a cell in the heap and also for updating cells in the heap. Okay, so once we have the notion of side effects, then it becomes important to be able to talk about a sequence in which expressions are being evaluated, right? So because if you have a notion of a producer and a consumer, right, you need to be able to say a producer needs to do its work first before the consumer starts consuming it, right? So you need to be able to say this expression needs to be done first before the other expression, right? It needs to be evaluated first before the other expression. So the question is, how do we realize this notion of sequence in the context of OCaml? Because up to now, we've just written expressions. We haven't really paid attention to the order in which expressions are being evaluated, but now the order has started to matter. Okay? So there are two ways in which you can realize this sequencing. One way is to use nested lets, which don't actually bind anything. So let's take an example that brings this out. Okay, so suppose the reference X that we had, what we want to do is, which was a pointer, which was a reference to a cell which had 5 in it, we now want to update it to the value in the cell to 7, right? And then we want to use the X in updating another cell that we might have declared, that we might have bound to a reference to, that we might have bound another identifier called Y as a reference to, right? We want to update it using the value that is stored in the cell named by X. So here's how you might do it, right? So what you're doing here is that you're evaluating this expression, okay? What you're doing is you're updating the contents of the cell that are referenced, that is referenced by X to the value 7, right? Once you're done, so that's a side effect. Once you're done with it, the value that is returned is of no interest to you, right? You just want to carry out the side effect. The value that's returned is going to the unit, and what you do is you bind it, right, in the let binding to some dummy identifier, right? Underscore stands for an unknown identifier because you don't care to retain the value that's, that is returned by evaluating this expression. Okay, so that takes care of the first bit, and then you get to the inner let, right? And in the inner let, now you can do the updating of the Y, okay, of the cell referenced by Y, right? So here you can use this side effect that was produced by the outer let, right? Essentially by looking up the X using the bang X, and the lookup will now look up the updated cell, right? And then eventually you set the cell that is named by that is referenced by Y to whatever was in X plus 2, which happens to be 9. Okay, and again the value that is returned by this expression is unit. It's of no interest to us, and there's no content in it. It's only being carried out for a side effect. So once again, we bind it to a dummy identifier or unknown identifier named by the underscore to it, right? And so those two lets have essentially carried out the two side effects that we wanted. And then after we've done that, then we can have whatever expression we want in the body of the inner let, right? And in this case, since it's a simple example intended to demonstrate the way you might realize sequencing, all that we're doing is looking up Y, and the lookup essentially returns the value 9, which is of type int, right? And OCaml is showing you that. Okay, so this is one way in which you can realize the sequencing, right? So we wanted to update X first, and then we wanted to update Y, making use of the effect of updating X. So in this context, you can think of the first thing as a process, which is a producer, is producing a value for X. And the second one is both as a producer and a consumer. It's a consumer of the value of X that was updated by the first producer, and it's a producer in that it's producing a new value for Y, right? So we can realize sequencing in this way. Right? Now, this is sometimes useful, sometimes it might be the most conspicuous way of realizing sequencing, but there's actually a much more explicit way of realizing sequencing in OCaml, and this is to use what is known as a sequencing expression. So what is this kind of an expression? It's something that we haven't encountered explicitly before. So in OCaml, what you can do is you can write an expression of the following sort, right? So within parentheses, you can have a bunch of expressions, E1 through En, each separated from the next by a semicolon. Okay? Okay, so what is the meaning of this kind of an expression? And the meaning of this kind of an expression is the following. It's basically saying that you should evaluate each of these expressions, E1, then E2, then E3, and so on, all the way up to En, one after the other. You should evaluate them in sequence. Right? And in the context of a sequencing expression of this sort, all the expressions like E1, E2, etc., all the way up to En, these are all essentially intended to be evaluated for a side effect. Okay? So eventually, when you evaluate En, we want this to be the value that is going to be returned by the overall sequencing expression. So the idea is that you carry out a bunch of side effects, and then eventually you want to return a value which is that computed by En. So the value and the type of the entire expression is essentially that of En, right? Following the logic through. So as an example, we might, the same example that we looked at earlier where we use those dummy lets, right? Lets that don't bind anything. It can be rendered using the sequencing expression in the way that I've shown out here, right? So the first expression is one which updates X, right? The second expression is one that updates Y, right? And once you've done both updates, which are essentially there only for their side effects, then you can have the actual expression that you want to evaluate based on the side effects, which in this case happens to be bang Y, and you get back what we got earlier. Something to note out here is that, as I've explained it to you, these expressions E1, E2, etc., all the way up to En, right? They are there essentially for their side effects. So OCaml expects them to be mainly side effecting expressions. So it expects them to be expressions that have the type unit, right? So if it sees that they are not of type unit, it will warn you that they are not of type unit. However, it won't raise an error in these situations, because sometimes you might really mean to have expressions in those places that compute a value for whatever reason, right? So it won't actually abort the computation. It will just warn you. Okay. So now that we have a notion of state, implicit in the discussion earlier is that the order in which expressions are evaluated becomes important, right? And in an expression like a sequence, in an expression such as nested lets and so on, the order is kind of explicit and we can realize it and pay attention to it, but sometimes the issues become a little subtle, right? So to highlight this aspect, let me look at a concrete example, right? So here's the example where I have a first let binding, which is going to bind A to a reference to a cell in which I'm going to put 1, right? Then I have another let binding in which I'm binding B to a reference to a cell in which I'm putting 5. Okay. And then I have a definition of this function called plus, right? It takes 2 arguments, okay, and it adds it basically produces the result by adding the two arguments. Right? Conceptually, it shouldn't matter when we're looking at a plus, the order in which we evaluate the two arguments that it's given. But when we have side effects, this starts making a difference. Right? So here's an example that brings it out. So we're thinking of evaluating plus, where the first argument given to plus is this expression, right? Which is a sequence expression. The first component of which is an update to A. Right? I'm going to update A to whatever we get from dereferencing the identifier B, right? Looking up the value in the cell that B is a reference to and adding 3 to it. Okay. So we update A, and then after the updating of A is done, then I look up A to get the value for the first argument of plus. Okay. And then the second argument of plus, I update B in this fashion, right? Look up the value stored in the cell referenced by A, add 1 to it, and change B to that value, and change the cell that is referenced by B to that value, and then I do a lookup of B. And the question is, what value will be produced? Now, if you look at, so clearly one of these expressions, this one, right, or this one, has to be evaluated first, right? So there has to be some order in which these things are evaluated. So if you think of evaluating this expression first, if OCaml will evaluate this expression first, we can try and figure out what the value is going to be. So A is going to be updated to whatever B contains, the cell referenced by B contains at this point, right, which is 5, which is 5 out here, right? So A is going to be updated to 8, and then you dereference 8, so dereference A, so you get 8, right? And then you're going to evaluate this expression, so the first component of which is you're going to update B to whatever is contained in the cell referenced by A plus 1, that happens to be 9. So this overall expression then is going to be whatever you get by dereferencing B, which is 9. So the value that would be produced if you follow this order would be 17. If you follow the other order, in the first instance, B would get updated, right, to whatever is stored in A plus 1, which happens to be 2, right? And then you get a 2 back from here, right? And then A is going to be updated to 2 plus 3, which is 5, and then you get a 5 from here. So 5 plus 2 happens to be 7, right? So what you see out here is that depending on the order in which the arguments of plus are evaluated, right, we get a different result, right? So one consequence of this is this idea that we were sort of paying attention, sort of following a fair amount, especially when you're talking about reasoning about programs, which is that we could replace parts of an expression independently of paying attention to which order the evaluation will take place. That breaks down a little bit, right? Okay, so that's the point that I'm making out here, right? The functional, what we talk of is functional elegance. This is lost, right? So we can't anymore think of replacing parts of an expression at will, right? We have to pay attention to the order in which evaluation will take place. This is if we have programs in which we are actively making use of side effects. Okay, so I should also answer the puzzle out here. Puzzle being, what does this expression compute to? Okay, and the hint here is that OCaml evaluates an expression of the form E1 applied to and so on up to En from right to left, right? So it will evaluate En first, then it will evaluate En minus 1 and so on. Then it will evaluate E1, and then eventually it will evaluate the entire expression, which is obtained by applying the function that comes out of E1 to all the arguments, right? So given that OCaml evaluates expressions this way, it's clear that this expression will be evaluated first, okay, and then we'll evaluate this expression. So the result that you get back in this case is actually 7, right? rather than 17. Okay, so that's sort of it's a uh, it's a detail, right? It's a detail about this example. The bigger point is that once we started introducing side effects, right, we can no longer retain the innocence that we had when we were talking about replacing subparts of an expression at will, right, without worrying about the order in which evaluation is going to take place. Okay, so it clutters up the space that in which we have to do reasoning about programs. Okay, once we have the notion of state, we can think of other kinds of constructs that we can import into the setting from other languages which have state, right? So from languages such as Java and C and so on, right? Imperative programming languages, right? And so these constructs, they ultimately are expressions, but they're expressions that return the type unit, right? So we can think of expressions that return the type unit as things that exist only for changing state. And these are what I had referred to a very, very long time ago as statements. So essentially, OCaml, once it has a notion of state, can also introduce statements, right? So let's look at a couple of examples of statements. So one of them is the if-then-else statement, right? Again, the if-then-else statement is a special case of an if-then-else expression, right? The if-then-else expression has a then and an else branch, right? And in the case of a statement, the then and the else branches will be expressions that have type unit, right? So the only purpose of the then and the else branches in the if-then-else expression that we're looking at, their only purpose is to carry out the side effect. So an expression that has an if-then-else expression that has a unit type then corresponds to an if-then-else statement in a language such as Java or C. Sorry, yeah, Java or C. Okay, so once we have this kind of a notion, then we can also think of an if-then as opposed to an if-then-else, right? Where the missing branch, the else branch, essentially is meant to do nothing, right? So we can, so OCaml actually has an if C then E1 kind of construct, okay, where it actually fills in with the else part with an else unit, right? Uh, and so this kind of, you can use this as an abbreviation for, you can use this expression if C then E1 as an abbreviation for this expression that is shown below out here. Right? So some of you who might have written an if then expression where the then part wasn't of unit type would have got error messages which would be saying that it isn't an expression of unit type, and hopefully you can understand where OCaml is coming from at this point, right? It's looking at the overall, the if-then expression that you've written. It was looking at the if-then expression that you've written, trying to treat it as an if-then-else and discovering that it couldn't because the E1 didn't have the type unit. Okay, so coming back to the top level, we have something like an if-then-else statement in OCaml. It's just an if-then-else expression whose type is unit, okay? Or alternatively, whose then and else branches correspond to expressions of unit type. We also have the familiar looping constructs in OCaml, like while and for, right? An example that shows you the use of the while loop is the one out here. So here I have a piece of code where what I'm doing is I'm setting x to a reference to 0, and then I have a while loop over here where I'm essentially incrementing the contents of the cell that x is a reference to each time around the loop till the value in that cell happens to be 5, right? So it's a meaningless use of the while. Is just intended to demonstrate how the structure of a while in OCaml is pretty much what you would expect it to be, right? So the while has a condition that governs when the loop needs to be continued, right? And then it has a body, and the body happens to needs to be placed between a do and a done, right? Um, which is like the curly braces in C, right? Okay, and then this is a let in which the body of the let itself is a sequence, right? So the first part of it is something that's carried out only for a side effect, right? At the end of the side effect, there's a particular thing that I want to look up, and that's what I'm doing up here. I'm looking up the value x, right? So the overall uh, let expression, this whole let expression, it's going to have the value 5, right? And that's what OCaml is showing to you out here. So the return value is 5, right? And the value returned from evaluating that expression is 5, and obviously that is a type 8. Okay, so there are a few other things like you have arrays in OCaml that have cells that are updatable. You have this for construct, which I haven't discussed or described explicitly. You can find more details about this in section 1.5 of the OCaml manual. Right? So there's a typo here. I should have the word manual following OCaml, right? But you can also sort of you can look it up directly, right, on the web, or alternatively you can just click the link that you see here, right, highlighted by the blue part, and you get to the relevant section, so you can read a bit more about these different kinds of constructs that are there in OCaml. Okay. I won't say anything more about these things. I want to switch now to talking about a slightly different but related notion, and this is the difference between implicit and explicit pointers. So let's talk a little bit to get to the right context for this discussion. Let's talk a little bit about how inductive data structures like lists and trees and so on would be realized in a language like C. Essentially, they are realized by pointers, right? So, for example, if you wanted to talk about a list type in C, here's how you define it, right? You'd say the list type, which in this case, so in C, I can't talk about a generic list type. I have to talk about a list type where the data that is stored is of a particular type. So I'll only be able to define something like an int list. So the int list type of here, right? The type declaration, this is a type def, is a type declaration, right? It's saying int list, it's a type, right? It corresponds to a cell, to a pointer to a cell, right? That contains some kind of data. And what kind of data does that cell contain? The cell contains, it's essentially a structure, right? One component that it contains is a field named head, in which you can store an integer. And then there's a tail, right? Which can store an int list. But the int list itself is a pointer, so it points to another cell, or maybe it points, it's a null pointer, right? So if it points to another cell, that tells you what the next cell in the list is going to contain, and so forth, right? So this is a notion of a linked list, which is what is realizing lists in C. And to realize it, you have to use pointers explicitly. Now, if you look at the way in which OCaml treats inductive data structures of this sort, right, where you have an object of the type which can be created by using a smaller object of that same type, right? You observe that we don't need actually to talk about pointers and references. These are kind of built in implicitly into the OCaml treatment of lists and trees and so forth. So what do I mean by saying that they're built in implicitly into the OCaml treatment? Well, let's look at something that mimics the declaration that we had in C, this declaration, right? So what we're going to do is we're going to use a record structure, right, for a cell which contains a head and a tail, right, as opposed to using a tuple the way it is done in OCaml, right? So how would I declare this type? Well, here's a type declaration. So I define a type called int list, right? where one component of int list, one possibility for int list is null, right? So this is one difference between the treatment in OCaml and the treatment in C. C doesn't give us something that is explicitly representing an empty list. Rather, you have to fathom that it's an empty list essentially because it's a null pointer, right? In OCaml, on the other hand, we have something that explicitly corresponds to a null list. And then you have something that corresponds to a list which has a head and a tail. That is realized by using this constructor called cons, okay, that takes an argument which happens to be something that is a structure, right? Something, a record, right, of type cell. And what is the type cell? It has a head component, exactly like we were seeing earlier, right? That is typed as int, right? And a tail, which is typed as int list. The thing to note out here is that int list is not really a reference, right? It's actually representing the data directly. Of course, in realizing integer lists that are defined in this way, you'd have to use some kind of a underlying linked list structure, right? But that's something that happens at the compiler level. At the language level, you are allowed to treat int lists as essentially in the form of the information that they contain. You don't have access to pointers to the cells and so forth, so you aren't able to change these pointers in any way, right? You just deal with the data as is. Okay? The other thing to note, of course, is that because in the end pointers were used for pretty much everything in OCaml, we can support polymorphism, so we don't need to talk only about int list. We could also talk about a list as a type constructor and allow the cells in the list to store objects of arbitrary type. Okay? So we have polymorphism built into OCaml, whereas C is unable to deal with this polymorphism, at least at the language level. Okay, so the point about this slide is that, or what we talked about in the slide is that where pointers are essential and need to be used explicitly in a language like C to realize inductive data structures, right? In OCaml, pointers are still used, but they are not they're not visible at the language level. At the language level, you're not talking about references and you're not talking about updates and so forth. Okay. So since pointers are implicit, you can't really modify existing objects, right? So if you want to generate a new, for example, think of append, right? You wanted to generate a list which represented the concatenation of the items in one list with the items in another list. You can't modify the first list in any way, right? What you have to do is copy the first list, and then once you copied it, then you can set its tail to be the second list, right? So that's how append is working, right? So you can't modify either the first list or the second list. You can generate a new list, but you can reuse the second list in constructing the object that you are generating. Now you might actually want to avoid this kind of copying, right? So in which case you can define a type. Now that we have references, you can define a type where the data components are made updatable. And you can use references to make it updatable. So as a concrete example, let's look at an alternative definition of the list type in OCaml. So what I could do is I could define a new type constructor called myList, which is parameterized by the type of the elements of the list, quote A, right? And the constructors for this list, for this type, one of them is nil, which represents the nil list, right? And the other one is cons, right? And cons now takes a pair. One of them is what you were thinking of as the head item in the list, right? And so it's the first item in the list. And then there's a tail. Now, in the tail, instead of using quote my list, what I'm doing is I'm using a reference to quote my list. So it's a reference to a list. Right? So if you use a reference in this way for the tail, then you can actually update the tail. Right? You don't have to create a new tail if you can actually update it directly in place. So let's see concrete. You don't have to create a new cell if you want to change the tail. Right? You can update in place. So here's a concrete illustration of this idea. Right? So uh, I begin off by setting by the identifier L, binding it to a list which has just the item 1 in it. Notice that in creating this object, I use ref nil because the tail has to be a reference, and in this case, it needs to be a reference to the nil list. So that's why I use ref nil out here. Okay, so that will create a cell in the heap in which nil will be stored. Okay, and then the reference to that cell will be placed out here. OCaml will respond saying L has been bound to something and so on. And what you can do now is you can let's say you want to update the tail so that you want the tail to become the list in itself, right? A list which has 2 in it. Okay, so here's how I might do it. So I can have a let expression in which the first part is matching this pattern pawns underscore t with L, right? So what happens as a result of this pattern matching? Well, L will be decomposed, right? We don't care what is stored in the head, but the tail is going to be bound to something. And what is it going to be bound to? Well, it's going to be bound to the reference to the cell of in which the tail of L was stored, right? Reference to the cell in which nil was stored. Okay. Okay. So then in the body of the let, what I'm doing is I'm updating the contents of that cell, right? I'm setting it to be a new list, right? I'm setting it to be cons of 2 with a reference to nil, right? So essentially, in place, I'm updating the tail of the list, right, to a new list, which is cons to ref nil, right? Okay, so the end result of this should really be that L has gotten changed, right? And we can see that out here. So what does L become? It becomes cons 1, so that's what this piece was, right? And then this piece which was ref nil, now that has got changed. And what has it got changed to? Well, it's got changed to something which is itself a list, right? It's got changed to something that is a list corresponding to something that has 2 as its head and nil as its tail. Okay. So we can, if you use, so what is the bottom line out here? Is that if I want to make my type updatable in place, I can use references like I've used out here. Okay, so just to come back to the top level, what we've observed is that at the outset, the way we've been treating data structures in OCaml, they are all immutable, and we can't change their components once they're set, although we can reuse in new objects that we create, we can reuse earlier existing objects. Okay. So the consequence of that is that our programs have the following kind of character. So give me a second because my iPad is running out of battery. I should connect it up. Okay, so I've done that in case I need to use it again. Okay, so think of append. Okay, when we're thinking of appending lists, we can, as I said earlier, a few times we can reuse old lists, and so we can reuse the second list, and we don't need to create it. But we cannot change them, so as a result, we have to make a copy of the first list, okay, of the cells in the first list, and then eventually finish off the list that we're creating by making it stale the second list. Similarly, if you're thinking of inserting in trees, right, we can reuse subtrees, right? So, for example, if you've changed the left subtree, you need to create a new node which has the data at the root and the new left subtree, but you can reuse the right subtree, right? But you can't actually change the old node to one which now stores a pointer, right, to a new subtree, the left subtree. Okay? But with the introduction of references, you can make these subcomponents mutable. So you might think of actually making changes in place. Right? And the question to ask is it a good thing to do this? At the outset, it might look like a good thing because you don't have to copy pieces, right? You don't have to, you can just make a change in place and then you're done, right? But it turns out that this is not necessarily a good solution, right? And it's something to pay close attention to. So let's spend a few words on this, right? So let's consider what kinds of differences there might be between using a mutable version of a data structure versus an immutable version. Okay. So here's one thing to know, right? If you want the behavior of programs to be predictable and modular, well, then you shouldn't actually change the input values. So more concretely, if for example, you take this expression, which is append L1 and L2, if after this append is finished, you still want to use L1 and L2, then if append has changed L1 and L2, you might end up getting garbage, right? So alternatively, if append L1, L2 actually creates the result of appending L1 and L2 by changing either L1 and L2, right? Then you have to be careful to prevent the calling process to not use L1 and L2 as if they were the original values with which append was called, right? So the bottom line here is that if you want predictable behavior, if you want the calling process to continue to believe, to be able to continue to believe that L1 and L2 were what they were earlier, right? Then you better not change the values. You can reuse because you're not going to change things, right? But when you want to create something new, something different, you better copy, right? Rather than, so L1 structure should be copied, but you can reuse L2. So this is a natural way of programming if you want predictable and modular behavior, regardless of whether you're using references or not. Okay. The second thing to note is that if the language doesn't enforce this structure, right? If it allows you to mutate the data structures, right? If you define the type in such a way that parts of it can be mutated, right? Then preservation of values has become discretionary. So you don't know when you make a call to append whether it has mutated its arguments or not, right? So reasoning about programs becomes a lot harder, right? Another way to put it is that this notion that we are referring to as functional elegance, it really has a significant impact on the reasoning process, right? Because functional elegance allows us to say that, once something has been set, it can't be changed, right? And so we can pretend that it's always the same value throughout, okay? And if you start using references that will allow you to possibly mutate, then you have to reason that the mutation hasn't actually been done in whatever you're trying to define if you want to be able to use this kind of reasoning pattern, right? So the bottom line here is that if you want this functional elegance, this ability to reason about your data structures in an effective way, then you'd better not use mutatable data representations. The last thing to note is that even though we might think that mutable data structures might allow you to implement things more efficiently, right? So for example, you don't need to copy the cells in the first list in an append. You just go down them and then make the last item a pointer to the second list, right? It might look as if it's more efficient, but in this case, there isn't a real benefit to the efficiency because you still have to go down the list. Maybe there might be situations in which the local operation in trees turns out to be more efficient, and you don't have to do a lot of copying. But in fact, I mean, these ideas don't necessarily pan out. Okay, so it's not as if mutatable data structures are really necessary for efficiency. You might have to think a little differently, right? When you don't allow for mutations, and when you don't allow for mutations, the data structures are what are referred to as functional data structures, right? So when you're using functional data structures, you can get efficiency, but you might have to think a little differently. Okay? And we won't talk a whole lot more about this issue of efficiency, right? We'll see how it works out in practice in a few cases. So for example, we'll talk about, hopefully before the semester is over, we'll talk about balanced binary trees, binary search trees that are called red-black trees. The canonical sort of the description of red-black trees that you would read in algorithms books, they typically use mutatable data structures, but we'll show how we can realize it pretty much as efficiently using a functional data structure. So we'll look at one or two examples of this sort, but for those who are really keen on finding out more about these kinds of things, I would highly recommend a book by Chris Okazaki that is entitled Purely Functional Data Structures. It's a book in which he talks about many, many different kinds of data structures and shows how using the functional approach, where you don't mutate data, it can yield perfectly efficient implementations of many kinds of things that we want to implement. Again, that if you on the slides on the course web page, if you click on the portion that is in blue, you'll be taken to a link on Amazon where you can look up the details of this book. I wanted to put a link out here to a copy in the library so that you'll be able to read it in these times when you can't actually venture out of home and you may not want to buy a copy of the book. It turns out that we don't even have a physical copy of it in the library at the U. There's a copy of it in, surprise, surprise, at the University of Minnesota at Morris. But you know, it's not very expensive. You can get a Kindle version of it if you're really, really interested in this. And if not, you know, once the semester is over and we're able to meet each other, you can stop by my office and I'll be happy to loan you a copy of my book. You can also do a web search. You'll find Chris Okasaki's thesis from Carnegie Mellon University that was an early version of this book, and you might want to look that up. You can download the PDF for the thesis, and you can look at it if the topic interests you. Okay, so that's about all that I wanted to say about the treatment of state. So we'll stop the lecture here at this point. In the next lecture, I'll take up the treatment of I/O in OCaml and also of exceptions. Okay, so that's it for today. Talk to you guys later.